Okay, this is Project Test 5, video number 2, and it's problems 11 to 20. A team of psychologists studied the effect of multitasking on the completion of cognitive tasks. A group of 40 women participated in the study. Each woman owned a smartphone equipped with the same type of keyboard. The women typed a text passage on the phone twice, one time while sitting in a quiet room and the other time while walking. Okay, so notice we're doing something twice. Each woman is doing it twice. Whenever I see that each woman is doing it twice, I'm thinking this is probably paired. The order of the single task was randomly determined for each woman. The psychologist recorded the time it took each woman to type the text for both tasks. If the conditions for inference are met, which of the following is the most appropriate to analyze the data? Okay, so we have a matched pairs test. I think that is the best because they were tested twice, right? Matched pairs test because they were tested twice. Number 12, the random variable x is normally distributed with a mean of 5 and a standard deviation of 25. The random variable y is defined by y equals 2 plus 4x. What is the mean and standard deviation of y? Now they're just doing this to try to confuse you by giving you multiple variables. Y equals 2 plus 4x. Well, we know the mean of x, so if I plug it in right here, I get the mean of y. So 2 plus 4 times 5, which equals 22. Well, that gets rid of a and b. And I want to point out to you that I can multiply measures of center by a constant, and I can add a constant to measures of center. So since we're talking about the mean, I can add a constant and I can multiply by a constant. The next thing they're talking about is the standard deviation. So once again, I'm going to write down the equation. So this is for the mean. Y equals 2 plus 4x. And they tell me that the standard deviation for x is 25. So I'll go ahead and plug it into the equation. Y equals 2 plus 4 times 25. Now I need to be really careful here. Yes, I can multiply measures of spread by a constant, but I cannot add a constant. So in this case, since I can't add a constant, the 2 goes away, and I'm left with is 4 times 25, which is y equals 100. And so my standard deviation is 100. All right, so number 12, the best answer choice is D. Number 13, in northwestern Pennsylvania, a zoologist recorded the ages and months of 55 black bears and whether each bear was male or female. The data is shown in the back-to-back stem plot. Now, please be careful. They've done this in kind of an odd way, where this is 15 months and this is 154 months. Okay? So basically, we have 15 months, 17 months, 18 months, et cetera, 20 months, et cetera. All right, based on the stem plot, which of the following statements is true? And this is F for female, and this is the M for male. The median and the range of both of ages are both greater for female than for male bears. Well, first off, what is the range? Well, we can sit there and go 154 minus 20. So 134. Here we have 70 minus 15, which is 55. So clearly the range is greater for the female. So the range is greater for female. All right, so that part's true. Now we need to check the median. Well, the median is the middlemost value, and I can eyeball this and get pretty close and guess on this one. I can guess that the median age for the females is probably going to be somewhere right around here, And for the males, I'm guessing it's over here, in which case the males is going to be in the 20 something and the females is going to be in the 30 or 40s. So it appears that females have a greater median age, but I can also count this out. So let's do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Okay, so 29 divided by 2 is 14.5. So the 15th one is the median age. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the median age for a female, the median equals 42 months. On the male, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So the male bear, we have 26 divided by 2 is 13. So between the 13th and 15th one, 13th and 14th one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So between these two, between 25 and 26. So 25 plus 26 divided by 2. So this is 51 divided by 2. So 25.5. So the median age for the male bear is 25.5 months. And the median age for the female. So the median age is greater for the female and the range. So the median age and range are both greater for the female bears. So consequently, our answer choice is A. So for number 13, the answer is A. Number 14, a producer, a produce supplier ships boxes of produce to individual customers. The distribution of weights of shipped boxes is approximately normal with a mean of 36 and a standard deviation of 4. So we have this mean of 36, and we have a standard deviation of 4. Which expression represents in weights at 75th percentile? That means this shaded area right here is about 0.75. All right. Now, whenever they give me a problem like this, I usually just write down z equals x minus mu over sigma, and I start plugging in to see what I know. Normal curve, that's just a good thing to start writing down. Well, I know my mean. All right. I know my standard deviation is 4. And we don't know this value right here at the 75th percentile. We don't know that. So that's x. But because we know this is 0.75, I can get a z-score. So second vars, inverse norm. And my area is going to be 0.75 because it's a percentile rank. And I end up getting 0.67, which makes sense that it's positive because we're over halfway. So 0.67. All right. So now let's do some algebra and rearrange. Well, I'm going to multiply both sides by 4. So I'm going to have 0.67 times 4 equals x minus 36. If I add 36 to both sides, I think you can probably see where this is going about now. We have 0.67 times 4 plus 36 equals x. And so they just basically tried to scare you by rearranging the z formula. That's all they did. Okay. All right. So our best answer for number 14 is in fact D. 15. A polling agency conducted a survey by selecting 100 random samples, each consisting of 1,200 US citizens. So they did 100 random samples. The citizens in each sample were asked whether they were optimistic about the economy. For each sample, the polling agency created a 95% confidence interval with a proportion of all United States citizens. Hold on a second. They did 100 random samples. So this is telling me that they're saying, you know what? In repeated sampling. Probably ought to remember that. Which of the following statements is the best interpretation of the confidence level? Oh, that's great. That ties directly to that. Because the confidence level is the statement in repeated sampling, we expect to capture the true population mean or the true population proportion about 95% of the time. And here we're talking about proportion. So with 100 confidence intervals, we can be 95% confident that the sample proportion of the citizens of the United States who are optimistic about the economy is correct. With 100% confidence interval, first off, that addresses the our conclusion. 95%, we are 95% confident that the true population proportion, but they use the word sample. We don't like that. So this is wrong because it's a true population proportion. We would expect about 95 of the 100 confidence intervals to contain the proportion of all citizens of the United States. In repeated sampling, we'd expect this to work 95% of the time. But since they didn't do all samples, they only did 100, they said about. This sounds like this is a pretty good possibility, right? Letter B sounds like a pretty good possibility because we would expect it to capture it about 95% of the time. It's going to work 95% of the time. We would expect about 5 of the 100 confidence intervals to not contain the sample proportion. If this is said population proportion, that would be correct. But since it says sample proportion, we don't like it at all. Of the 100 confidence intervals, 95 of the intervals will be identical. No, they won't. All samples vary. That can't be the case. The probability, and immediately when I say the word probability, I don't like it, but we'll go ahead and read it, is 0.95, that 100 confidence intervals will yield the same information. They're not going to yield the same information. We're 95% confident that they will contain the population proportion. In fact, they use the word sample. So this is a no-go all the way around. So in this case, since we did it over and over again, we did it 100 times, we would expect about 95 of them to capture the true population proportion. If we did it an infinite number of times, we could say that it would capture it 95% of the time. All right, number 16. As part of a national sleep study, a random sample of adults was selected and surveyed about their physical activity and the number of hours they sleep each night. Of the 183 who exercised regularly, 59% reported sleeping at least 7 hours a night. Of the 88 adults who did not exercise regularly, 52% reported sleeping at least 7 hours a night. Which of the following is the most appropriate standard error for a confidence interval? This is important for the difference in proportions. All right, so for a confidence interval, we're going to go ahead and write down the interval, the equation. So p hat 1 minus p hat 2 plus or minus z star p hat 1 q hat 1 over n1 plus p hat 2 q hat 2 over n2. And they're asking for the standard error, which is this part right here. If I include the z, it's the margin of error, but if I'm looking at just this part, it's the standard error. All right, so we have 0.59 times 1 minus 0.59, which is 0.41, over the 183 plus 52%, so 0.52 times 0.48 over, and then we had 88. And we just need to put this under the radical. All right. So with that answer, we go, okay, I can see real quickly that my best choice is answer A. So for number 16, the answer is A, but I want you to be really very careful about this. Had this been a hypothesis test, this formula would have been different. Because remember, a hypothesis test for the same thing, and I'm going to go ahead and use a different pen on this so that we don't get confused. A hypothesis test would have this formula. We'd have p hat 1 minus p hat 2 over the square root of p combined q combined in 1 plus p combined p hat and then q hat combined over in 2. And we'd have to remember that p hat combined equals x1 plus x2 over n1 plus n2. And this becomes really a challenge with this problem, and I'm going to go ahead and work this all the way through just because I don't want this to happen to you guys. So we're going to go back up there, and we had 59% out of 183. So p hat 1 equals x over n, which in this case equals, which gives us p hat 1 equals x over n, and p hat 1 is 0.59 equals x over 183. So when I go ahead and solve that for x, 0.59 times 183, I end up getting 107.97. You are going to have to round if you get, if this becomes, if you get a decimal answer, round. And so I'm going to round to the nearest, which is 108. So x equals 108. So basically we have x over 183. So all right, I'm going to go ahead and write that down over here. I'm going to have 108 and then a 183. And I'm going to put a plus and a plus. Then I need to come back and do p hat 2. P hat 2 is x, once again, is x over n2, and p hat 2 was 52%, equals x over 88. They had 88 people in that sample. So 0.52 times 88 is 45.76. And once again, I'm going to roll round to the nearest whole number. So x equals 46. So I'm going to come back over here and I'm going to go 46 over 88. And I know that this isn't part of this problem, but I'm telling you, I want you to make sure that it doesn't mess you up because it has shown up on other exams. So 108 plus 46 is 154. And we have 183 plus 88 in the denominator. So 154 over 1 over 271. 154 divided by 271 gives us about 0.57. So p hat combined is about 0.57. Q hat combined would be 1 minus that, which is 0.43. So p hat combined is 0.57, q hat combined is 0.43. And when we plug into this formula over here for our standard error, which is this part down here at the bottom, we end up having 0.57 times 0.43 over N1, which is 183, plus 0.57 times 0.43 over N2, which is 88. And I don't know why they like to do this to us. I think they want to show that we're mathematicians too. But they like to factor out the numerator. And so they're going to go, okay, if I factor out the numerator, I can write it just like 0.57 times 0.43 times 1 over 183 plus 1 over 88. And if I use distributed property, I'd get back to that same thing. Now this right here, either one of these represents the standard error of a hypothesis test. So if they'd asked for the standard error of the hypothesis test, we should be looking for one of these. And in fact, had you done the standard error of the hypothesis test, they had it. Okay, so this is the standard error of the hypothesis test, is answer choice C. But they asked for the confidence level, which is a lot less work, and that answer choice was A. But you do need to be able to do both of them, which is why I took the time to do that. All right. Problem 17. A representative of a car manufacturer in the United States made the following claim in a news report. 10 years ago, only 53% of Americans owned American-made cars, but that figure is significantly higher today. A research group conducted a study to investigate whether the claim was true. All right, so first off, if they're making this claim, HO P equals 0.53, HA P is greater than 0.53. That would be our null and alternative. The group found that 56% of a randomly selected sample of car owners in the United States owned American-made cars. A test of the appropriate hypothesis resulted in a p-value of 0.283. All right, so we have a p-value here, 0.283. Assuming the conditions for inferences were met, is there sufficient evidence to conclude at the significance level of alpha equal 0.05? So here's our alpha level, 0.05, make them the same length. And this is clearly greater. So because this is greater, we fail to reject. So there's not sufficient evidence. All right. So what is our decision? The question is there sufficient evidence? And the answer is no. There's not sufficient evidence because 0.283 is greater than 0.05. So our answer to 17 is E. Number 18. Researchers wanted to investigate whether babies have a sense of right or wrong. They showed each of the 60 babies a puppet show in which a red puppet was trying to open a heavy box lid. A second puppet called the helper would try to help the red puppet open the box, while a third puppet called the hinderer would try to slam the box lid down. After watching the show, each baby was presented with a tray containing the helper puppet and the hinderer puppet. And the researchers recorded which puppet the baby reached for. The researchers wanted to determine whether the babies would reach for the helper more than for the hinderer. As part of the show, a green puppet and a yellow puppet served as the helper and hinderer. So, for each baby, a coin was tossed to determine which color would serve which role. Which of the following is the most important reason for random assignment of the color? Basically, we're randomly assigning the color because we don't want it to be a confounding factor. We want to know whether or not the baby is choosing the helper because they're helping open the lid, or whether they just choose the hinderer. So, slamming the lid might cause wear. No, that's not what we're worried about. The puppeteer might grow tired of doing the same show. I hope not. These are kind of ridiculous answers at this point. If the same role is played by the same color puppet, the babies might show a preference for the color. In other words, color may be confounded with the type of puppet, may be confounded with hinderer or helper. And because it might be confounded, that might be the reason. It's like if they prefer green, which they probably do, then they're going to choose the green puppet regardless of what they're doing. So it's very important that we isolate that. Nineteen, nutritionists examine the sodium content of different brands of potato chips. Each brand was classified as healthy or regular based on how the chips were marketed to the public, not on what they had, but how marketed. The sodium content in milligrams per serving of the chips is summarized in the table below, in the box plots below. All right, so we have the regular chips, sodium content, and we have the healthy chips, sodium content. Based on the box plots, which statements give a correct comparison between the two classification of sodium content of the chips? First off, the number of brands classified healthy is greater than the number of brands classified as regular. Well, we have no idea as to how many brands were classified as healthy. This could be 10 and this could be 100, or this could be 100 and that could be 10. They didn't give us that information. We don't have a sample size. The IQR of the brands classified as healthy, so this brand, so here's my IQR, the disc right here, is greater than the IQR of this brand. And yes, this brand definitely is less than the healthy. So healthy has a greater IQR. 19 is B. Number 20, a factory has two machines, A and B, making the same part for refrigerators. The number of defective parts produced by each machine during the first hour of operations is recorded on 19 randomly selected days. The scatter plot shows the number of defective parts produced by each machine on the selected day. So right here on this day, we had 2 by A and 4 by B. Now I'm going to tell you, when they give a scatter plot like this, I really think it helps to take the moment to draw a 45-degree line. So I'm going to go ahead and draw a 45-degree line. Just because it kind of gives me an idea of what's going on. Which statement best gives the best comparison between the number of defective parts produced by the machines during the first hour of operation on the 19 days? Well, real quickly, I noticed that machine B is above machine A, which means machine B has more defects in general. More defects, machine A has less defects. Now, this isn't completely right because we can sit there and say, hey, right there, machine A definitely had more defects. Machine A always produced the same number of defects as machine B. And the answer is no. If they did that, then they would be right on the 45-degree line. So that's false. Machine A always produced fewer defective parts than machine B. No, didn't always. Machine A always produced more defective parts than machine B. That's false too. Machine usually, but not always, produce fewer defective parts than machine B. Usually, yeah, most of the time, but not always. So 20 is D. All right. 20 is D. Thank you.